I just want to thank the organizers for the opportunity to talk and for this great conference. Okay, so let's see. Is this right? Okay, so the aim is to model quantum phenomena using degenerate spacetime metrics. In particular, somehow incorporate quantum non-locality into general relativity. So this is kind of the idea. And the second thing is to resolve the measurement problem in kind of quantum foundations, which is what causes wavefunction collapse using spacetime geometry. So with these aims, the proposal is that the preparation and measurement of a quantum system are simultaneous events. And so I consider this proposal by modifying classical general relativity so that there are no distinct points in the world lines of dust particles. So that is, time does not advance along the world lines of dust particles. And just before I get in, just to give a little background, so I do algebraic geometry, and this comes from looking at what are called nonnoetherian coordinate rings. It comes from something looking at non-superconformal quiver gauge theories and string theory. But then I was taking this geometry with these nonnoetherian coordinate rings and trying to apply it in the context of GR. And so the idea is you have two entangled particles. They fly away from each other, but they still remain correlated. So how can you have a space-time description of this? And the idea is that time isn't flowing along the world lines, so that they're kind of single one-dimensional points. And so in space-time, these two particles flying away from each other would make like a V shape. So even though they appear to be, however far separated, they're still next to each other in space-time because their world lines are single one-dimensional points. Okay, but so on the math side, it comes from looking at non-noetherian coordinate rings. Okay, so let M tilde G be an orientable Lorentzian four-manifold and consider a set of dust particles on M tilde with world lines beta I. And we call this set M obtained from M tilde by replacing each of the beta i's by single one-dimensional points in internal space-time, or simply space-time. And we call M tilde the external space-time of M, and the dust particles pointons, because their world lines are points. So a couple of things. So let beta be the world line of a pointon. Then we cannot define a tangent vector along beta in M, since beta is a single point of M. Second, beta is a continuum of distinct zero-dimensional points in M tilde and a single kind of one-dimensional point in M. And the thing is, we don't, so in geometry and topology, when you take a quotient, you contract, say, your curve to a point, zero-dimensional point. But in this case, we're not doing that. We don't throw away M tilde in constructing M. So M tilde is our four-dimensional normal, just Lorentzian four-manifold, and M is our new sort of geometry. So therefore, to construct an internal metric, we'll call it H, at a point P in M tilde from the external metric G, it must project out each vector V tangent to a geodesic point on world line beta at P. So also, please stop me if there's confusion. Is a little bit odd at first, but it'd be better for me to make things more clear than to get to the end of my slides. So if there's questions, please stop me. Yes. So this is, well, I'll define a metric in the next slide. Maybe we'll see. Ask me again and just see if it answers, and if I don't, then ask me again. Yeah. Yes. 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 So time isn't flowing along these world lines of these dust particles. So yeah, so the idea is you're to try to describe quantum non-locality, so say two entangled particles um, from this construction. So this is the basic idea. Yeah. Okay, so recall the orthogonal projection of a time-like unit vector, just shown there. We will describe the projection when V is null shortly. So our definition is, so fix a point P in M tilde. We call the metric G an external metric at P, and let V1 through Vn be the tangent vectors to the point on world lines beta 1 through beta n at P. So we can have however many of these world lines intersecting, and we define the corresponding internal metric to be the degenerate symmetric rank 2 tensor given by the composition of projections. So they're built from G, but we're projecting out the tangent vectors to these point on world lines. And we define the internal tangent space, which is tangent space at P, to be the image of H at P. And so I denote the tangent space, which is M sub P. So this is the internal tangent space, and then M tilde sub P is the four-dimensional tangent space from M tilde, from our four-dimensional manifold. Okay, so now where do we go from this? So just a quick review of orientation and Hodge duality. Yes, yes. M tilde. We don't throw away M tilde. So we can still say, we have the kind of these two spaces sitting together. So this is the difference between just a quotient, say, where we would throw away M tilde. We still keep M tilde, but we just say time isn't flowing along these world lines. And so, but we can still say, we want to ask what happens at this event in M tilde, and say these world lines intersect. And so what is going to happen is we have H is a degenerate space-time metric. So just as it, as is given here, so it's a projection onto the subspace. It's a subspace projection. So if you think just an isolated particle here, one of these dust particles, and it has this world line just going like this. Its tangent space along this world line, as it's an isolated particle, would be three-dimensional. But if it intersects another one, then it could go to, say, one dimension or two dimensions. So the dimension of the tangent spaces change. But the idea is that this is going to cause wave function collapse and things like this. So the idea is to describe quantum phenomena with this variable tangent space dimension. This is no, but please keep, yeah. Yeah, so for our purposes here, this is, in say the setting where you want to include quantum field theory, this is, I don't know yet, but for what we're doing here, just is a discrete set. So just a finite set, for example, of these, or countable, discrete set, yeah. Yeah. Okay, so just a quick review of orientation and Hodge duality. An orientation of a vector space V is given by fixing an ordered basis B of V and declaring any ordered basis to be positive, respectively negative, if it can be obtained from B by a base change with the positive, respectively negative determinant. And Hodge duality, so this is, you have, say, E naught through EM is an orthonormal basis for V, for vector space V. Then the exterior algebra has bases consisting of one of the set of these volume forms. And in particular, the volume form for the whole space is just a wedge product. Yeah, it's an element of this exterior algebra. And the Hodge dual, so star psi of an element psi in the exterior algebra, is defined on the basis elements just as usual. So psi wedge star psi is proportional to the volume form of the whole space. And this is extended R multilinearly to the exterior algebra. And for example, star of 1 is the whole volume form. So Hodge duals capture orthogonal subspaces. So if V is R3, then the Hodge dual of E3 is E1 wedge E2, or -1 wedge E2, with the sign depending on a choice of orientation of V. So Hodge duals are pseudoforms, and that is, they depend on a choice of orientation since they are defined using the volume form. And so, yeah, just think of Hodge duals as kind of, it generalizes cross products. So it captures orthogonal subspaces. Okay, so now we don't have tangent vectors or four velocities anymore with these particles. So what do we replace them with? Consider a pointon with a time-like worldline beta and four velocity v on m tilde. Since v is projects to 0 under h, we want to replace v with a new geometric object, we'll call it v check, that is intrinsic to spacetime m and independent of m tilde. So we may replace v with the Hodge dual of the volume form of the kernel of h, since each one form in this Hodge dual lies in the internal tangent space along its world line. However, a Hodge dual is a pseudoform and thus depends on a choice of orientation of the kernel of H. So to eliminate this dependency, we allow an orientation of the kernel to be freely chosen, independent of any non-physical choice of orientation of m tilde. So we're getting by, the idea is by each vanishing subspace, we get a free choice of orientation, and we're going to identify these free choices of orientation with things like electric charge, color charge, spin, things like this. So we'll get physical properties from these just orientations. So orientation plays a big role here because somehow we need to define things and we get these free choices of orientation. So we define the internal four velocity of a pointon with worldline beta and four velocity v to be the pseudoform. So write v check, where, so this O subkernel of H is plus or minus 1 is a free parameter independent of any orientation of m tilde, and times the Hodge dual of the volume form of the kernel of H. And so the rank of this pseudoform changes along the world lines as the pointon may intersect other, so the world lines may intersect, and then the rank of this pseudoform changes whenever the dimension of the tangent space changes. Okay, so let beta be a time-like pointon worldline with four velocity v, and let E naught through E3 be a tetrad along beta for which E naught is equal to v, and fix a point P along this worldline. If the dimension of the internal tangent space at P is 3, then the internal four velocity at P is a free choice of time orientation, O naught, and so in the rest frame of the pointon, times E1 wedge E2 wedge E3. And we identify this time-like orientation with the electric charge of the pointon. And this is very similar to the Stuckelberg-Feynman interpretation of antimatter in quantum field theory, where antimatter flows backwards in time. But in this case, time does not flow backwards along beta, just as it does not flow forwards, since beta is a single point of space-time. But it's similar to the Feynman-Stuckelberg interpretation of antimatter. So this free choice of time orientation for E naught, we identify with the electric charge. Okay, if the dimension of the tangent space at P is 1 and the kernel of H is spanned by, for example, E naught, E1, and E2, then the internal tangent, the internal forward velocity is O naught times now another parameter, a free choice of orientation of the plane spanned by E1 and E2. So we call this O12 times E3. So it's an honest vector or one form. And we called this the spin vector of the point on that P, and identify this free choice of orientation O12 as spin up or down in the E3 direction. So we then parallel transport the spin vector along beta until it is projected under H onto a subsequent one-dimensional tangent space. So this spin vector we get from a one-dimensional internal tangent space. And if it goes, if we have this line, so if it goes this way or this way, that's the spin. And that's the free choice of orientation of O12. So it could point in, one or two, there's two possibilities. And so that gives us a spin, and the spin is in that direction of this one-dimensional line. Then we parallel transport this vector along beta. Okay, so now consider a point on with spin vector S and worldline beta such that the dimension of the tangent space at beta of 0 is a local minimum along beta. If the length of h of s is non-zero, we denote by h hat its normalization. So as s enters, so the spin vector enters this lower dimensional tangent space at beta of 0, S is projected onto it by the internal metric H. And we identify this as spin wave function collapse. As H of S exits this lower dimensional tangent space to a higher dimensional tangent space, a section must be chosen, and the reverse occurs. So a unit vector S prime is chosen such that this condition here holds, or equivalently, it's just that H of S dotted with S prime is non-negative, and we identify this with the randomness in the outcome of a spin measurement. So this choice of section. And this condition here in 2 simplifies to just saying the normalized projection of S and S prime are equal whenever the projections are non-zero. And if H of S equals 0, then S prime is unconstrained. And if H of S is non-zero in this case, then or if H of S is non-zero, so S doesn't project to the 0 vector, then the probability that S prime is chosen is given by what we call the Kochen-Specker conditional probability. And so this is going to reproduce the Born rule for spin wave function collapse. And so it's just that it's given by the dot product of the normalized projection of S with S prime. Okay, so for example, if H of S points to, say, the North Pole, so this is our spin is in the direction of, we have our block sphere, a sphere, and H of S points to the North Pole in this unit sphere in the pointons rest frame, then S prime will be some vector in the northern hemisphere, with it being more likely that it's pointing to the North Pole than to the equator. So that's all it's saying, but this is the new spin vector we get when we leave this smaller dimensional tangent space and go to a higher dimensional tangent space. So then we'll show that this gives a realist non-deterministic model of spin without physical spin superposition. But of course, this is still a non-local thing in the sense that time isn't flowing along these world lines, so points are connected to each other from this geometry. And in particular, spin superposition in this model is epistemic, which means a spin wave function represents our knowledge about a state, but is not an actual physical thing. And this is not to be confused though with path superposition, which is a whole different story. Because this this S prime, so the reverse of so when we go to a smaller dimensional tangent space, we project the spin vector onto the lower dimensional tangent space. When we leave the lower dimensional tangent space, kind of the time reverse occurs, and so a section is chosen of this projection map. So, there's an arbitrariness, and the probability is given by just the dot product. So it becomes less likely, but the reason this has this form is that then this will produce exactly the Born rule for spin wave function collapse. So you get quantum mechanics out of this. Yeah. 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 No, definitely. Yeah. So that's exactly what this is describing. Yeah. So, yeah. But I mean, my thing is I love geometry and GR, and I would rather change quantum stuff to fit GR than the other way around. So this is my personal thing. So that's what kind of the aim is here. To model things in quantum world by using space-time geometry. Yeah. No. So this so far, there's nothing, I'll get to entanglement later and give an example. But for this, there's no, you just have a photon, say, or an electron, whatever, sorry, not photons yet, an electron, and it has its spin, and its spin vectors. So the projection that you get from wave function collapse is the actual projection of one tangent space onto another. So it's the projection you get from wave function collapse in this setting is just actual, projection from one tangent space to another. Yeah, so that's, but I'll get to entanglement soon. Okay, so suppose S exits a one-dimensional tangent space at P, and M tilde is parallel transported along beta for some time, and then enters another one-dimensional tangent space at Q. We say the spin of the pointon is prepared at P and measured at Q. So preparation and measurement in a quantum system, in this case, we can say exactly what this means explicitly in terms of space-time geometry. The vector h hat, so this normalized projection of S at beta of T, sits in the unit sphere parallel transported along beta. And this sphere corresponds to the spin Hilbert space, so this two-dimensional Hilbert space for spin, there's this usual correspondence with the Bloch sphere. And so we just take this usual correspondence, and we may thus identify this sphere that we parallel transport along the world line with the Bloch sphere, and therefore the projection of S at P we identify with the ket of its normalization, and the projection of S at Q with the bra of its normalization. And so our theorem is that our model is the space-time geometric realization of something called the Koch-Specker model of spin, and therefore reproduces the Born rule for spin wave function collapse. So we get exactly the Born rule from this setup but this gives a space-time description of it. Yeah. Okay, so now we go to the case we had before. So when we had our projection, V was a space-like vector, but if it's null, of course, the projection we had before doesn't work, doesn't project out the vector. Easy lemma is just let V be a null vector, then any minimal orthogonal projection of V is going to, you can write it of this form. So it projects out a two-dimensional subspace where V prime is a null vector that contracts with V to give -1. And then you can show that the internal four velocities of V and V prime are equal up to sign. So one is the negative of the other. Okay, so the theorem then is that a pointon with a null geodesic world line cannot exist in isolation. So it has to be paired with another pointon. And it has to be paired with another one of opposite charge. So this is a theorem. And the bound state of the two null pointons then necessarily has 0 electric charge. So this very naturally leads to some identifications where we say, okay, a pointon is like an electron. If the orientation of E naught is future directed, then it's an electron. If it's past directed, it's a positron. And if you stick two of them together, then we get a null geodesic, and we can identify this with a photon. It's neutral, so it has 0 electric charge, and it's a bound state of an electron and positron. So this is a composite model, but again, all we have is just space-time so far. So we're just playing with space-time, but we're seeing some other things come out of it. So here's our electron, our positron, and our photon. And then this would be a picture, so time going in this way. This would be an electron and positron annihilating to give a photon. This would be a photon decaying into an electron and positron. Here you have an electron absorbing a photon, and here you have an electron emitting a photon. So it gives a very picture view of what happens when an electron, say, emits or absorbs a photon. Okay. Yeah. So well, time isn't flowing along the world lines, but to make a to project out a null vector, you can't just project out a one-dimensional. Your subspace you have to project out at least 2 dimensions to project out the null vector. And so what happens is you can't just have one pointon by itself. It has to be paired with one with the opposite time-like orientation. And so therefore the opposite electric charge. Yeah. I see. So just the way I've drawn, this is maybe a bad drawing because this should be at a 45-degree angle. Is that, yeah. No. It's just to draw it so it fits on this slide. So, I mean, in a second, I'll also let these be time-like. So it's an off-shell photon. So I'll allow these bound states to be both null or time-like. It's just these can't be null. Okay, so now consider 2 pointons of opposite charge with coincident world line beta. The pointons form a photon along beta, which is on shell if beta is null, and off shell if beta is time-like. Okay, so if we have this bound state together, it will be, depending if it's time-like or null, says if it's on shell or off shell. Oh, so on shell, I should say, in any, say in a Feynman diagram, any trivalent vertex where an electron and photon interact, always one has to be off shell. You can't have all three to be on shell. Off shell means relativity is violated. And I'll get to this later, but it's basically a violation of relativity. It's saying, yeah, I'll get, I'll try to get to this, but when a particle is on shell, it means relativity is maintained with this momentum, momentum. And if it's off shell, then relativity is being violated in the Lagrangian picture of in quantum field theory. Okay, so the pointons each have an ontic spin vector denoted S plus and S minus. So we have the future directed pointon world line and the past directed one. So we have two spin vectors. And now the idea is, okay, if this is a photon, it should have polarization. So we have these two spin vectors, and how do we get polarization out of just parallel transporting two vectors along a geodesic? So, we impose the following conditions. So one, the dot product of these two spin vectors is non-negative. So S minus could go with the one with the, say, past or time-like orientation, and S plus with the pointon with the future directed time-like orientation. And second is a point P is an endpoint of beta if and only if the dimension of the internal tangent space at P is 1. And this is the same thing we had before, the same condition, but we see it again with we impose this hold for these spin vectors. And this just simplifies if the projections are both non-zero, then all this condition says is that the normalizations of the projection at P are equal. And this will say if we'll make a model of spin 1 polarization from these two spin vectors. Okay, so the theorem is that suppose there's an electron-photon vertex, so one of these, like the pictures we had before, at a point P and M tilde, then the dimension of the internal tangent space at P is 1 if the photon is on shell, and 2 if the photon is off shell. Consequently, full spin polarization wave function collapse can only occur at vertices for which the photon leg is on shell. So this has to do with why we don't see these kind of virtual particles, these off-shell photons. Suppose that an on-shell photon meets an electron at a point P and M tilde in for example, a linear polarizer. So we have a polarizer, light's going through it. The internal tangent space at P is in one-dimensional by the theorem. This is conditioned that the normalized projections of S minus and S plus being equal determines whether the photon will pass by the electron with no interaction or interact with the electron at an electron-photon vertex. So in the first case, the photon passes through the polarizer with these two spin vectors altered by the one-dimensional tangent space at P. In the second case, the photon is absorbed by the electron. And so consequently, this condition that the normalized projections of S minus and S plus at P being equal determines whether the photon will pass through or be absorbed by the polarizer. So it's a geometric condition that says whether the wave function collapse will occur or not. So this condition says if it's met, wave function collapse, or for polarization, the wave function will collapse, and if it's not met, the wave function will not collapse. So it's a geometric condition to say, whether wave function collapse will occur or not. Okay, so suppose a photon has spin vectors S minus and S plus, and consider this line formed by the span of their sum. And this is a subspace of the internal tangent space along this world line for the photon. Further, suppose the photon meets an electron at a point P and M tilde for which MP is a line. Then an electron-photon vertex will occur at P if and only if the minimal angle theta from negative pi to pi between the parallel transport of L at P and the line, this subspace MP, the internal tangent space at P, satisfies the condition that this angle is less than absolute value than pi over 4. And so let S minus and S plus be the spin vectors of a photon, and let phi be the unique oriented angle between negative pi over 2 and pi over 2 from S minus to S plus in the plane spanned by these two vectors. We say the photon has linear polarization given by the line, that's the line L, and left respectively right circular polarization if phi is positive respectively negative. A photon thus has at all times both a well-defined linear polarization L and circular polarization given by the sign of phi. So a measurement of one renders the other random and unknown. So this is kind of what you can picture. There's different ways you can have these two spin vectors. And so, okay, how is this related to classical polarization for photons, right? We have an electromagnetic wave. So in terms of classical electromagnetic theory, phi equals 0 corresponds to linearly polarized light, equals plus or minus pi over 2 to circularly polarized light, and generic values of phi to elliptically polarized light. How is this related to polarization in the quantum setting with our two-dimensional Hilbert space? We'll consider an on-shell photon with null 4 velocity v given by E0 plus E3, and denote by H the Hilbert space with basis vectors E1 and E2, and pH is projectivization. We map the polarization states non-injectively to states in this projectivized Hilbert space as shown here. And with this identification, we recover the Jones vectors for photon polarization. So we exactly get the quantum mechanics of photon polarization from having these two spin vectors. So it's a different model of what photon polarization looks like. It's not electromagnetic waves. It's not in a Hilbert space. It's just parallel transporting these two spin vectors and projecting them into smaller dimensional tangent spaces. And maybe, so maybe I'll stop here as my last slide because of the time. And leave the rest for another time. But I just want to say a word about entanglement. Okay, so consider two photons emitted from an electron. Right? So here we have an electron, then it emits a photon, goes along and emits another photon, and then goes on its way. Well, see, the red line is all connected. So this is one point in space-time. So the photon's polarization may remain correlated because they share a common point on world line drawn in red. And thus we obtain a possible approximate geometric model of entanglement. So this is, of course, very different from non-separability with tensor products. But we have a geometric picture of entanglement, and there's things like, for example, entanglement swapping and different scenarios where you can do a similar model and it all works out the same. But this does not work in all cases, so this is different in general than normal entanglement from quantum mechanics. But so this one would be like a Beil type correlation with two photons. So we can reproduce lots of things like this, but not everything. So if each photon encounters a polarizer, then the two polarizers are effectively still touching, regardless of how far apart they appear in M tilde, since the point-on world lines are single points in space-time. And the caution is that we expect that geometric entanglement will only approximately reproduce quantum entanglement. And so quantum theory in our model will differ in certain situations. which is good because then it's something to test. So, okay, so I just go, so we did this with electrons and photons, and then the next question is, what about all the other standard model particles? But that will be for a different day. So I'll just go here. So these papers are just on this geometry in the setting of algebraic geometry and what's quiver representation theory. And the top two are, yeah, the stuff I talked about in this. Okay, thank you.